Meiklejohn. I'm a PhD student in Belgium in Louvain-la-Neuve. And I do not like RPC. I feel like there's an A meeting for, but for distributed programmers or something.
These are little stretch bus, okay. So I'm Caitie McCaffrey. I'm a distributed systems engineer. I'm here to provide the industry perspective on all of this and keep it a little practical. This is where you can find me on the internet. I work at Twitter now. I've been building distributed systems for a while. Please give me a shout out if you have questions or anything after the talk. Okay, so just before we dive into RPC, we're going to talk, I want to make a quick distinction between what is actually a distributed programming language versus a concurrent programming language. Because in industry, you sort of hear the two terms conflated, and I think there's a very important distinction. So the concurrent programming is this idea that computation can make progress without the one before it finishing. So we can do things multiple times. It doesn't necessarily mean in parallel. It just means things can advance without waiting for everything before it to finish in a sequential manner, or not in a sequential manner. And then distributed programming is this idea that we can accomplish things via networked computers. So they're going to go out across the internet. You're going to do a bunch of stuff, and then somehow you get a result back from that. You need concurrency in order for distributed programming to be practical, because otherwise you're just sitting there and blocking and waiting for all these machines to do something, and that would be super inefficient. But they're actually fundamentally different. Concurrency primitives are fundamental to running multiple things at once, and then there is the idea of distributed primitives for a distributed programming language. So to make this a little more concrete, we're going to go through some examples that are currently being used in industry today. So Nojs is very popular. It's this framework written in JavaScript. It is a concurrent programming language, and even though it is only single-threaded, because it has this event loop, and so you do things, and then when they have to go and do something that's somewhat asynchronous, you have a callback that can happen. So when you're making a network call, it has a scheduler that can invoke something else happening. So you have this interleaving of requests, even though everything is single-threaded. But when you have to go make that network call to your database or to another node process, there's no primitive in the language to help you do this. Another super popular language right now is Golang. It's actually being talked about very often as a distributed systems programming language, but I don't actually think it meets our criteria, because really it's a concurrency language. It has concurrency primitives in these Go routines, which are basically very lightweight threads, and it has its own scheduler, so it can schedule things. And it can actually take advantage of multiple cores on a machine, and then it uses channels to do, which is based on top of CSP, and that's how these processes can communicate with each other. So this is basically a concurrency language, or has concurrency primitives, but I wouldn't call it a distributed language. So the core concept with a lot of these, and there's a bunch of things that have concurrency primitives baked into the language, is how do you communicate with code running on other machines? And all of these languages that we've seen have basically left that as an exercise for the reader, and so that's why I'm saying they're not meeting our bar as a distributed programming language.
Okay, so I'll talk about Erlang. You've probably heard of it, maybe. So Erlang is a concurrent language designed for highly concurrent telecommunication systems that was designed in the 80s and kind of built upon since then. And so it uses the actor model for concurrency, and so you spawn a bunch of lightweight processes which represent actors in the system, and then these actors will exchange messages asynchronously. And what's important about this model is that there's no shared memory, so state is kind of explicitly sent through messages, and you kind of have process isolation. And then you have a scheduler that will run a bunch of these in parallel and kind of do preemptive scheduling for those processes. And so what's notable about Erlang is that initially designed as a concurrent language, it was later extended for distribution. And so in that extension, which we refer to as dist or distributed Erlang, you were able to send messages to processes that could be located on other machines. And so the system would transparently take care of forwarding that message to the other machine and attempting kind of a best effort that that message would get delivered. And so the process identifiers encoded a location on the network where that process was living. And so you didn't have to think about sending messages, manually marshalling and sending data, opening a socket, right? And so, there's been a bunch of languages that have been extended with actor model for distribution. So one notably is Cloud Haskell, which is an extension of Haskell using the semantics that came from a paper that was written about what Erlang's distribution semantics were. And some of these couldn't be directly implemented because there's a little bit of a type difference between these two languages, and so there were some things that had to be slightly changed. But so this is similar, and in the similar way, you can look at languages like Termite Scheme, which is another example of a language extended with primitives for doing this type of thing.
Cool. So now that we have that distinction, so that we understand that what we're talking about with distributed programming languages is that we want these primitives that help us talk to other computers in a network. We're going to talk to something that came out early in the distributed programming language sort of research space called RPC, or the remote procedure call. So the basic idea and the fundamental principle here is we want to make remote calls, or ones that go cross-address space, basically look just as simple as programming local calls. So that's the goal of RPC. So today here's a quick path of where we're going. We're going to go through all of these sort of like RFCs and points in time where RFC was defined and there were different critiques. And then we're going to come to present and like what's happening in industry today. And then we'll talk about, is RPC a good paradigm, or is this one that we should continue or be happy with? And then we'll talk about some future research in the distributed programming languages space that is maybe challenging this notion that RPC is the way to do distributed programming.
Okay, so the first paper, RFC, I guess, request for comments, that we'll talk about is from 1974, which is actually a series of RFCs about about the procedure call paradigm, or PCP. And basically this is kind of an important paper in the lineage because it establishes the idea that on the internet we have a bunch of machines and we'd like these machines to be able to share resources. And so we have to find a way to do this. And so at this point, they focus around procedure calls, so that you would want to remotely invoke a procedure call that would do something. And this would be done, this could be accessing a shared resource, or it could be kind of sharing information with another node. That's kind of left open. And so this is important to look at here. It was defined across all 70 nodes of the internet. So this is like node DNS. This is host files. Like this is, I'm in the NSF and you're at Stanford Research, and like maybe I need to get some file to you somehow, or we need to collaborate on something. But what's important about this is it kind of sets the stage for this entire lineage of papers that we'll discuss. And so, the first, so RPC is interesting because it's kind of it's kind of like a 30-year, 40-year rap battle between like academics and industry people and vice versa. And so this is kind of the first of 3 papers in that epic rap battle. And so this is RFC 684, which appears the following year. And so RFC 684 is basically just a critique of RFC 674. And it talks about a lot of things, and these things that you're going to see are repeated across all of these critiques, but I'm going to highlight 3 of them. So the first one is the acknowledgement that a local call versus a remote call is going to have a different cost profile. And so the realization here is that if I make a local call, this is going to be a context switch, something's going to execute, and then control flow is going to return to the invoker. Remote calls don't always work like this, right? Systems could be partitioned. I can make a call, that system could disappear. It could send me a message, but that message might not be delivered because, I don't know, networks are unreliable. And, local calls usually have some sort of fixed latency profile, right? And, if we think about, having clocks, we approximately can guess how long a computational step will take. And so remote calls, because of latency, can take, this arbitrary amount of time. We don't know. And so having a system where a remote call can appear as local, you may program some application where you're like, I'm just going to do this thing and then I'll do something else, I'll wait. And your program may never finish, right, if you never get that message. And so this is kind of the second point that's highlighted here, is that remote calls can be delayed, they can never return, and we have a variety of kind of impossibility results in the academic space that kind of show that failure detection is really hard in partially synchronous systems, and asynchronous systems it's impossible to solve. And so this is a challenge in trying to make something that has a whole nother domain of failure kind of appear oh, it's just local, it's fine, just think of it that way. And so this paper is kind of the first to propose that asynchronous message passing, or assuming that, I'm going to send some message and later I may get some response, but I'm not going to wait for that response immediately. And sending kind of a message rather than building an abstraction on a procedure call where I assume I'll invoke this and immediately get a response and then continue programming in a sequential manner. that asynchronous message passing is probably a better way of building these systems. And so we see this in Erlang. Erlang is an example of a language that under distribution has asynchronous message passing. Now, if we move a little bit forward to RFC 707, in 1976, RFC 707 says a couple interesting things that I'll highlight. So around this time, we have protocols like Telnet that runs on port 23. We have FTP that runs on a different port. And the realization that this RFC makes is that, well, all of these protocols are really the same thing. We could implement them all by RPC, right? So it says, well, Telnet is a call and response protocol. You write something, you get some response back. FTP, you say user, get an OK, say password, get an OK. SMTP, hello, OK, right? All of these protocols have this call and response, and why can't those messages, those specific grammars for each of these protocols, why can't those just be a function call? And so this proposes kind of a generalization to say that, well, what we can do is we can just make this grammar a grammar of functions, and then we can implement all of these things in terms of RPC. Regardless of, outside of the idea that a lot of these protocols we wanted standardization, that was the whole point of the RFCs and the IETF, right? And so what you can kind of see a little trace of this historically, because if you look at systems that implement Sun RPC, you'll see like things like rlogin and RSH. A lot of these things, they all use the RPC facility to run in the language. They all use a port mapper. But they are kind of different protocols, and you can kind of see this historically. And so this paper, while admitting this, it still critiques control flow and says, well, we still have a problem, right? Call and response is bad because if I go to perform some action, I have to wait for that to complete before I perform the next action. So it limits the ability for me to do operations concurrently. It makes sequential composition challenging, or concurrent composition. And finally, it doesn't allow priority servicing as well. In case, I want to, for instance, handle some requests earlier because of some quality of service metric or something like this, right? So it doesn't support priority servicing. It inherently is like a request response cycle. Okay. All right, and so 1984, this is like the big paper in the field, Burrell and Nelson, 84. This is work that, that's been the culmination of the Cedar RPC system at Park. This becomes later the Sun Microsystems implementation of Sun RPC, 1988 with RFC 1057. And so this is kind of the paper that is the standard design of what you would want from an RPC system here. And so this
but now project management comes in, and there has been some change where now it has to run across multiple machines. And so we're like, cool, no problem. This was written using RPC, so we should be able to do this seamlessly and distribute the code across multiple nodes in a network, and it should work, right? But the problem is basically what they're saying is the chances of this working is not good. Because RPC fundamentally ignores a lot of things about how remote procedure calls look when it talks to another node. Like there could be failure, that the network is asynchronous, and that you have partial failure. They're relying on the fact that we can't actually know when failures happen. We don't have a reliable failure detector. And all of these things, whenever you actually run this stuff in the real world, doing this and having it work is not going to fly. And so that's sort of if we had a correct RPC system, all the tests would still pass in this mode. So they point out this fundamental flaw where they're basically saying there is no protocol that can perfectly guarantee that both sides of the RPC, both machines in the remote procedure call, definitively and unambiguously know that the RPC is over in the face of a lossy network. So this is hearkening back to something like the two generals problem, right? Unsolvable in an asynchronous network. This is because we don't have perfect failure detectors. This is the FTP result. So they're basically pointing out that this is a problem of distributed systems, and RPC has not even attempted to solve it, and so it can't be the correct model going forward.
Okay, so we'll talk about NFS. So how many people here remember NFS? Show of hands. All right, great. So I worked in telecom. I was an admin of an NFS server, so I guess you could say I've been fighting RPC my whole life. And so 1989 RFC 1094 defines what we refer to as the network file system protocol specification implemented by Sun Microsystems. Sun had the Paramount implementation until later. Linux got an implementation. And so the idea of NFS is that I should be able to mount a remote file system, and using the existing file system API, I should be able to interact with it. And so anybody who's actually used NFS in the real world knows that there's lots of times where you'll like cd into a directory and type ls and it hangs because you can't talk to the other node, right? And so this is a problem. And what this problem comes down to is this dichotomy between soft mounting and hard mounting that is critiqued by Waldo many years later in 1994, who was also at Sun Microsystems. And the challenge here is that NFS had two modes. So the soft mounting mode said that there's a bunch of failures that can happen when you are actually working with a distributed file system. And so what we can do is expose a series of new error codes that will represent like, oh, you know, there was a timeout, or I couldn't do this, or I couldn't do that because of various reasons. Now the problem with soft mounting, and the reason it never got adoption, is because no tools, like for instance an LS or something like this, or touch or whatever, none of these tools would have compatibility for this API. They just wouldn't be able to handle these new error codes coming from the file system API. So soft mounting doesn't really get adoption, but soft mounting is the idea that we'll treat the resource as remote, but we won't be able to leverage our existing application, right? Our existing Unix applications that work with the file system API. Oh, and so the opposite side of this is hard mounting, right? And so hard mounting says, well, no, we won't add any new error codes. We'll just block, right? We'll make every call synchronous. We'll block, and we'll wait for things to return. And so this is the reason you have cding into a directory and typing ls, and then your terminal hangs, and you have to kill it. You can't even control C out of it because you're in some IO, you know, blocking mode that you can't interrupt. And so this is the challenge here, right? And so we see that the developers, as a developer, I want to leverage existing infrastructure, existing tools. I want the hard mounting solution. I want the transparency. I want the unified model. I don't want to deal with soft mounting because I have to make everything handle kind of remote cases or some subset of it, right? And so, you know, a few years passed, and we have this thing called korba. How many people here remember korba? Almost the same amount of people. It's great. I love that. I got a boo. Was that a boo? I hope that was a boo. But and so 1991, we have korba. And the Common Object Request Broker architecture, back when like acronyms like this were super cool, which was probably never. But and so the goal of korba is this idea that we want to support calls cross-address space, so multiple machines, no shared memory. We want to do this across different languages, so Java, C++, C, whatever. And it's going to be for object-oriented programming because, you know, it's 1990, so object-oriented programming is the thing, right? And so, kind of like microservices are the thing now. And so the idea here is that the first challenge we have to deal with is this idea of an interface definition language, right? So if I'm going to transfer an object, like an int64 from C to, you know, C++ to Java, I have to deal with like some sort of like type conversion, right? I have to know how to serialize this correctly, deserialize it correctly. And so I have to have a mapping between these types across the machines, across languages. This needs to be for objects and primitive types, and so this is kind of a challenge. And so actually, Steve Vanoski, who usually comes to these conferences, but not anymore, wrote an article called "It's Just a Mapping Problem," and who actually wrote the korba book. So this is kind of a great, you know, moment of changing your mind, I suppose. But and says that, you know, the challenge here is that can we map things that are remote to local? Can we map these exceptions? Can we map exception handling? Can we map types? Can we do all this stuff? And so the answer sort of ended up being no, even though korba, I believe, is still going today. And one of the major articles that challenged this, which is probably one of the papers that has been very influential to my own career, is this paper from '94 by Sun Microsystems Laboratories by Waldo and his group here, called "A Note on Distributed Computing." Right? What a great title! It's just so, I don't know, so perfect. And so this paper challenges NFS, it challenges korba, it challenges everything. And so at the time, korba is remote method invocation, basically the same thing as RPC in many ways, and so it applied to objects. And so this paper makes an observation that the dream of korba, as stated by this paper, is that what we'll do is we're using object-oriented programming, so we'll write an application, and what we'll do is the natural interface for the application will fall out because that's the promise of object-oriented programming, which we realized is not right. And so they say first the natural interfaces will emerge from the application domain because objects talk on application boundaries. It's nothing to do with technical implementation details, another thing that we know is not true. And then they say, well, what you do is you take that application and then you just move the objects around the network to find the best performance. So to think that we can apply, an NP-hard optimization problem to figure out the best distribution of objects on a network that's rapidly changing and asynchronous and can fail all the time, that's kind of a thing we know is also not true. And so kind of all of the basis on this application design is kind of fundamentally flawed. And the reason that they want to do all of this is because they want to achieve what's referred to as the unified model. And so we see here this quote, Waldo, just drops the mic right here and walks away. It is the thesis of this note that the unified view of objects is mistaken. Straight up, you're wrong. And he says this for a few reasons. And so these aren't new. You should know this. This is a familiar theme. This is paper 3 of the epic rat battle here. And so we can see latency. Well, we know that latency is not going to be the same. We know that latency is a problem. We know that operations are going to take a lot of time. And we kind of need this to be explicit to build a system that performs well. The second is memory access. So how do we deal with pointers and references? So if I have an object and I want to send it to another object, like through a method invocation, well, what do? Well, I can serialize the object and serialize the class and deserialize it on the other side and build an appropriate class on the other side. But then what if that object references memory? So then I can serialize all of the objects and I can serialize all the references and send them over the wire. But then what if I'm using relative pointers? Well, now I have to deserialize it and make sure that all the memory lines up so that all the relative pointers stay the same. And geez, this sounds really hard too, right? So, maybe we just copy everything implicitly, right? Why not, right? The network's free. And so finally, kind of the last bit here is that partial failure. I can send a message to somebody, and they might process it and send me a response, but maybe they die right before they send me the response. So do I wait forever? Does that method called wait forever, or does it time out? If it times out, does it throw an exception? What's that exception, right? Can I retry it? So that's an interesting question that we'll come back to. And so Waldo identifies that there are 2 paths forward. It says you treat everything as local, you get your unified model, or you treat everything as remote, and this is sort of how distro works with some exceptions. And so to kind of wrap up this, this paper, I think this, I'm just going to read this directly because I think it's just so important here and so clear, and I couldn't say it better. This approach would defeat the overall purpose of unifying the object models if we treat everything as remote. The real reason for attempting such a unification is to make distributed computing more like local computing, and thus make distributed computing easier. The second approach to unifying the models makes local computing as complex as distributed computing. So he kind of challenges this, what did we get? What did we get? If we do everything as remote, it's all clear, but did we really gain anything? Okay, so we left in the 90s, and now we're at the present, about more than 20 years later. So I'm going to start with a little story about some of my development history. So I used to be in video games, and I worked on the Halo franchise for the Xbox. And the way that our Xboxes communicated with our services, I worked mostly on the services side, was they would send C++ structs that happened to be ripped out of memory with padding, compiler padding, in big endian, and they sent it over the wire to a C# server with little endian architecture, and then we had to deserialize it and write code to do that. So that was obviously awful and never broke. We'll just come back to that story in a second, but there was a gap where basically RPC had kind of died, and we were doing this crap. Also because there's only 256 megs of RAM on the Xbox, and we weren't allowed to use it for the network because of graphics, but whatever, that was a thing. And then you see all of REST and everything had gone sort of away from RPC for a long time. So now we're in this world. You have microservices, or whatever buzzword you want to call it now. But there's a bunch of things, there's a lot of complexity to our applications today. We're all building distributed systems today, essentially. And in addition, they all basically are written in different languages because reasons. Sometimes it's happiness, sometimes it's performance, sometimes it's newfangled shiny thing. But this is actually not crazy. This is what a lot of stacks look like, I would think today. And so because of this, we've seen the reemergence of what I'm going to call RPC frameworks in quotes. And we'll get to that. So one of the big problems these things are now trying to solve is that all of these are generally running within, when you deploy software in a data center. Making HTTP calls is expensive because of strings, and doing all of that is doing the network negotiation is expensive. So we'd like a more compressed framework. We need to figure out how to find and talk to all of these microservices that are running, and we need to do this translation between different language spaces, right?
So we're going to go through a couple. I'm going to spend the most time on finagle because I think, I come from Twitter, and so this is pretty core to how I build services today, and I obviously have the most experience with it, but there's a lot that are very similar. So finagle came out, and it was an RPC system for the JVM. It has an interface definition language, which is thrift. And so what it does is that helps us map between different data types. This is an idea that came from korba. It basically takes the space of, it punts on this idea of like, how do we deal with like memory access and pointers by just copying everything. So it sort of punts in that field. It then also solves the problem of service discovery. So how do we, which was not addressed in a lot of what we went through today, because it wasn't as big of a problem, I think, at the time when you only had like 70 computers on the internet. But now, like actually knowing where this machine is running and wanting to do continuous deployment, that thing's not static. A static DNS is not probably going to fly if you want to bring machines up and down and like have tens to hundreds and scale elastically and all those nice buzzwords. So we need some way to solve this. So finagle solves this by plugging it with service discovery. It does a lot of really nice engineering to sort of figure out if there are bad machines and siphon off requests for them. All of that makes my life as a developer a lot easier because I don't have to write this for every single service we deploy. And they also solved, applied promises, which was not a new area of research. This is another area of distributed systems programming that Chris has a great blog post on if you want to read more on the history. But they applied this to like RPC. So that you could solve this control flow problem, so that we don't have to sit there and just like wait. We can actually fire off a bunch of requests, have a promise for the result, and then like execute on the promise and compose them and do all of these nice things. So this is super nice. This is actually really useful. This is a much better world than me having to like convert C++ structs in C# in different endianness. This solves that problem for me. It also solves the problem of like, where do these things live? It doesn't solve all of the problems, right? I would say that like, as a developer, when I'm writing an IDL or writing a finagle service, I'm not actually like writing finagle as like every functional interaction. I know that when I like have a finagle request that I'm making, that it's going across the wire. So implicitly, like we have now decoupled sort of this model of what I program locally from what is remote. It looks very different, right? It also like will give you like things like timeouts and retries and all of that you have to specify on your own. And so like another good story sort of from my career to highlight this is I was working on observability at Twitter, and we had a problem where our service grew by an order of magnitude, and so all of your performance calculations and things are now wrong. And so we basically were doing a lot of work on the services to make it more robust and more reliable, and one of the things we noticed is that whenever our data store happened to hiccup briefly, or like go even close to its SLA and start failing a few requests, we'd have this enormous backup in the metric ingestion service, and you would sort of see the JVM get really sad because there's all this memory now, and they would sort of die, and it was bad times. And you get paged, and I didn't like that. So what we did is we went and we spent a good about a month tuning the retry policy and actually reducing the consistency level because we didn't need as strong a consistency guarantee as we were using. And this actually made it much smoother so that the network could hiccup or like our data store could hiccup, and it wouldn't cause a huge problem and affect our service. But this was like a month worth of my time basically retuning something that in the theory of like what we tried to set out for RPC should have been solved. So finagle does not solve a unified model. gRPC is the other super popular one right now. It comes from Google. It uses an IDL, which is protobuf. It has more language support because it's not just based on the JVM, and it also supports bidirectional streaming, which is pretty different. And it also, I believe, has a pluggable infrastructure for plugging in service discovery and how you know where machines live. But they're pretty similar. It's just like choose your flavor of like what language and environment you like. I haven't worked with this extensively, so if there's something that I totally missed, sorry. But what this all comes down to, and what I'm trying to get at, is that modern RPC frameworks don't provide a unified model, and they never tried to. So are they really like RPC frameworks in the sense of what we started with? You know you're going over the wire. And so this gets back to this fundamental quote from a note on distributed computing, where Waldo says, the hard problem in distributed computing are not the problem of getting things on and off the wire. And I would like to posit that these modern RPC frameworks are only solving the problem of getting things on and off the wire. Not that this is bad, or I would like to not live in a world without this, right? Like, I don't want to go back to that world where I have to serialize all this. This is an excellent piece of engineering and a fundamental building block of how we do communication. But that's the problem it is solving for us, is getting things on and off the wire. It isn't solving the problem of, like, what if it fails? Is this request idempotent? Can I retry it? How long should I wait for it to fail, right? Like, what do I do? It's not solving any of those problems for me. I, as a developer, still have to understand all of this. And it's definitely not even trying to provide a unified model. So it's just a building block to make, you know, an API or a library to make my life better so I don't have to like open sockets and do all of that on my own. So realistically, right now, we have a bunch of concurrent programming languages and a bunch of RPC frameworks, and we're gluing them together, and we're making distributed systems, and life kind of sucks. So I would like to posit that maybe we need something better. And to close this out, the idea is here is like the point of RPC was to make remote calls just as simple as local calls. And if we treated everything as remote, then we haven't really simplified distributed computation at all, which is why you don't see gRPC and finagle trying to like unify the model. It doesn't make it any simpler. It actually makes life a lot harder, so that's why they stay at the boundaries. And then if we can't treat all calls as local, if this premise is fundamentally wrong, is the procedure call actually the right model that we want to keep going with in the future for distributed computation? Do we need something else, and what might that be?
Okay, so I'll briefly tell you, this is the section where the academic gets to plug his own research. So I'll briefly talk about, I'm going to briefly talk about 3 things, and I'll focus on the last one a little bit more, because it's a little bit closer to practicality at this point. But, and so the challenge, one of the challenges that Caitie highlighted with finagle is that if we need to be able to retry operations, we need operations that can be safely be retried, right? We need idempotent operations. If we have fewer network guarantees, we need operations that are commutative. And so there's been a bunch of work in the area. I have some work that I've been doing as part of my PhD called on a programming model called LASP that only allows you to write programs that are safe where operations can be arbitrarily reordered, rebatched, or replayed. So you lose a lot of expressive power in your language. You can do fewer things, but all of the things that you'll do are basically safe by construction, correct by construction, as we call it. And so that's kind of one area that's being researched. Now, somewhat related to that is the work on Bloom by Joe Helisian's group at UC Berkeley and now Peter Alvaro's group at UC Santa Cruz. And what Bloom and subsequent version BloomL try to do is build languages that minimize coordination. So what they try to do is say, well, this operation is commutative and this is idempotent, and so we can do these operations without any coordination at all. These languages allow you to express more because you can express things that don't have those properties. And then what the language will attempt to do is draw a nice little graph that shows you here and here you need Zookeeper, for instance, because this program will not be safe under distribution without an order, or something like this. And so Peter's approach has the ability, so to contrast these approaches, the last approach makes is reduced expressivity, but everything's correct by construction, where Peter's approach is making an arbitrary program and then having an analysis tool to tell you where you can weaken things. And so these are kind of complementary approaches. The final piece of work that I'll talk about is work by a friend of mine, Heather Miller. She spoke here last year. I believe she spoke directly about this topic, possibly. And she spoke about her work on a library called Spores, which is around serializable closures. And so Heather's work is kind of she likes to call it a dual to the actor model, so a dual to something like Erlang. And the idea here is that rather than have actors or processes use asynchronous message passing to move data around the network, what you'll do is you'll move functions around the network instead. There's challenges around this, as we saw with something like korba, right? And so you can't get a closure that closes over some global memory reference or a reference to a global object in the global namespace, singleton object in the global namespace. And so there's challenges. And so what you do is you use a type system, such as the type system that Scala provides, to ensure that everything that you attempt to capture with the closure can be safely serialized. And then you know that that closure can be arbitrarily sent to any node on the network and execute fine. And so to kind of see where something like Spores could be applied practically and was being researched in the context of, we can consider a system like Spark. And Spark is a system for doing large-scale data analytics. It's kind of the natural successor of Hadoop because it actually addresses failure and performance. And so the idea with that is that you perform function composition. So I have some data set, and I say I'm going to map it, filter it, fold it. And then what will happen is when you go to read that value, it will be realized by moving the functions around, computing a new piece of data that represents the result of this computation. So data in this model is immutable, persistent data structures. And so this is kind of an alternative way that's trying to say, well, can we take a step back and look at how we're trying to build distributed computing systems and maybe look at different paths. And so all three of the work I demonstrated kind of try to address all of those problems.
Cool. So that's our talk. We hope you learned a bunch about RPC and maybe challenged your notion that this is the one and true way going forward, and hopefully gave you some hope at the end so you're not just stuck. All of the resources in the papers and things mentioned for this talk, including slide links, are on my GitHub repo, so feel free to check that out. I'll also tweet it out after the talk if you can't read that. And thank you, and we'll take questions now.
Thank you for the talk. Do you have any examples of people using any of the three sort of future technologies right now?
Do I have examples of people using the three future technologies? So if we go back to the future technologies, so I can speak a little bit. So I don't know if Spores actually made it. Oh, I'm using both mics. I don't know if Spores actually, if that work actually made it into Spark, but it was being researched jointly by EPFL and Databricks. So there was an intention to put it in there. I don't know if it made it, but very much that model can be used in that context. It was designed specifically for that. I don't know if somebody's adopted the research library, because research code is usually terrible in many ways. In terms of the Bloom work, the analysis code that Bloom uses to identify those coordination points, that analysis has been used in another piece of work, so not about programming, but about system composition in a system called lineage-driven fault injection, which actually is being talked about. Somebody at this conference is talking about it. I don't know if it happened already or not, but Shanti Allen is talking about it. And so the analysis code has been repurposed because it's a general logic for identifying places that are unsafe without ordering. And so you can use this in other contexts. And then my work on LastBiz is built on top of conflict-free replicated data types, which Martin talked about in his talk earlier today, and there was a workshop yesterday on it. And so those CRDTs have been tremendously successful, I guess, for research that's fairly new in industry. So it's used by Bet365, and it's used by Basho and React, and it's used by Rovio and Riot Games and League of Legends. So the data structures that prohibit the composition, the data structures that give you the safety properties are used independently, but as of now, the research that we're doing is purely a research prototype that does not have any industrial adoption yet.
Yeah, I think it's also worth mentioning, like, we didn't put async message passing on this slide, but I also still think, and you can contradict me if you disagree, but async message passing is probably a better thing than RPC.
Systems like Orleans as well are tremendously successful in getting people to build really correct distributed applications with the actor model. So
Orleans is interesting because it sort of merges. Orleans is an actor framework. I used to work on it when I was at Halo, but it actually merges this idea of the actor framework and async messaging with a little bit of RPC, because it does have this idea to do a call and response, or you can just do a fire and forget message. So to simplify some of the programming model, but you still very much know you're making an asynchronous call that may go over the network.
Can I ask a question, since I have a mic and everything? What are your thoughts on AWS Lambda, and how does it fit on what you were talking about today?
So I haven't used it.
What was the question?
AWS Lambda. What do we think about AWS Lambda? And serverless, I guess, is maybe the hashtag you're getting at.
Yeah.
I'll give you my perspective from industry. I think it's really good that we're simplifying the operational cost of having to do and deploy something. Like iterating really fast is like what I want, right? Like this is where I'm saying like finagle and gRPC are like foundational building blocks. I do not want those to go away. They make my life easier until we get something better. And Lambda is sort of like that. Lambda doesn't address anything with distributed computation, though. I actually have a tweet conversation where I was talking to people at the serverless conf, because I didn't realize it was getting retweeted on the stage. But it was basically this idea. I was like, well, what do you do? Because I just heard of it, and I was like, what is this? And I'm like, well, what do you do with your state, right? Like, how do you store your state? Because they basically had this slide that was like, distributed systems are solved. And I was like, that sounds like magic and ponies, and I'm all about those things. And they were just like, well, you store it in, you store it in S3, or you store it in Dynamo. I was like, why am I blanking? Like listing every other key value store in my mind. And that's still a distributed system, right? Because you have to make a call that could fail or not. And so you still have to understand some of it. So I think, I think Lambda is great because it reduces the operational burden that it takes to deploy and run code. I do not think it solves anything with distributed systems.
Yeah, I was just going to remark about your comment about like where you store the state. I talked to somebody who said, oh, I built this stateless infrastructure with AWS Lambda and DynamoDB. And I said, how does it work? And they said, well, Lambda gets an input from the database and then writes an output to the database. And then the next input is read from the database and written to the database. And I'm like, God, that sounds like the state monad. It sounds very far from stateless, doesn't it? Yeah, but Lambda is challenging because I think that once you start putting all of your data everywhere, now consistency is a huge problem. And there's only been about like 3 researchers, I think, probably historically, who have ever considered consistency in programming languages. But as we start putting stuff everywhere, I think that's a problem that we really need to start considering. So hopefully there'll be a revival of that, because it was popular many years ago.
Well, thank you very much.
Cool. Thank you.